Okay. So yeah, we're going to kind of take this one at a time. So we're not doing neighborhoods right now. What we're gonna do is calculate some zonal operations, right? So right now, pretend that this is this other layer right here. The ratings towns is the ratings for the overall ratings. So we want to ask the question: which of these potential parks? I just made this at the beginning of the break. These are potential sites to put a park. And we want to know which one has the highest suitability. Well, in this case, it'll be, did I get rid of that other one? Yeah. So what we're going to do is find out which one has the lowest values. That'll be the best one, because in this case, the high values mean not suitable. Okay? So which one of these has the lowest overall value? So we want to run a zonal operation, and the zonal operation will tell us, of these potential park sites, which one has the lowest overall value in terms of its. We're going to do the average. Let's do the average first. So we'll find the average value of all of the cells that are within this park, all the cells within this park, all the cells within this park, and so on. All right. So how would I do that? Well, I can run the geoprocessing tool. I'm going to go into the toolboxes, and this geoprocessing tool is referred to as the. It's in the zonal tool set right here. I told you that the most common ones would be tabulate areas and zonal statistics as table. Those are the two most common ones. Zonal histogram will produce a bar chart of the frequency of all the different values within the data set. Zonal statistics will be a data set that is actually a raster data set. In fact, I'll run that one first. Okay, I'm going to run zonal statistics first. So here I input the raster or feature zone data, which in my scenario that I've just come up with, what do you think is the zone data? Yeah, the weird shaped things that look kind of like squares. Yeah, the potential parks. The potential parks are the zone data. Now the zone field, that's in the data, particularly if it's a raster data set, particularly if it's a vector data. It's a raster data set, it's just going to use the raster value. It'll turn that to value. But if it's a vector data set, you'll be allowed to choose which field represents which field represents the zone. Okay? Because you could have some text data in there, and you could have lots of other things. Here we're going to use the object ID. It'll just be the unique identifier. So every single thing that's kind of like a square up there will have its own object ID, and it'll have its own value, and they'll be calculated for each one. So input value raster. What's the input value raster going to be? The town ratings, the ratings. And so what it's going to do is find all the cells within here, and it's going to calculate the mean. So when I run this, I'm going to call this something better. I'll call this zonal statistics mean parks, and run this guy. I'm going to create a data set there it is right there. So it's below my potential parks. So I got to turn off my parks. And then, I'll leave the ratings on. Okay, so the values are now the same everywhere within the park. And outside the potential parks, we just have no data. So can we tell easily which one is the one with the lowest value? I mean, it's hard to kind of tell. Let's see if we change the symbology a little bit. The ones in the black have the lowest value, so they're the best. Yep. How did I create the polygons? And I'll show you that. All right, there it is displayed differently. So now it's a little easier to tell. I think this one has the lowest value. We could inspect it. So that one has a value of 4.21. This one has a value of 3. Oh, so that's actually the lowest. So this one has the lowest mean suitability rating. So that one is the one that's least affected by the town's suitability model. Okay. All right. So how did I create this? Maybe I should have recorded it, but I didn't. The first thing I did was say new feature class. And then I walked through this wizard, and I made sure that I chose, so I'm going to call this delete me. Then I didn't change this at all, but if I wanted to make my new data set have fields, I would have added new fields here, but I didn't. Yeah, I just drew them. Just for an example. And then I hit next, and then I made sure, what I did was I went in here and chose import coordinate system, and I made sure to pick that I was in the same coordinate system as the town's rating data set. And then I hit finish. Finish. So now I have my delete me data set, and I dragged it onto the screen, and then I started just drawing. Did you guys do that in your Intro to GIS class? Maybe not in ArcGIS Pro. You probably did it in ArcMap. But the way you do it in ArcGIS Pro is you go to the edit. See, this might not be. If you hit edit, then you can hit create, and it will allow you to draw on that delete me data set. So I could draw a polygon. And then you go to save, and that'll save the polygon that you just created. If you want to create more, you can. I'm going to get rid of that one. So yeah, sorry, that wasn't included. This was kind of like a spur of the moment raster. Zonal operation map. All right, now, in reality, that may not be the answer that you always want. You might want a table instead of these values, because there's no table. Even if we open up and we say right-click and hit properties, right-click, there won't be the ability to open up the table, attribute table. There's no attribute table. Why is there no attribute table? Because it's still a floating point raster. So there's no attribute table. Okay? So what we could do is run a different tool called zonal statistics as table. What this is going to do, we're going to select the exact same inputs. Potential parks. We're going to select the rating towns. And instead of the output, I'll just call it zonal stats. I'll call it mean parks table. Right. So now when I run this, oh, by the way, you can select any statistic you want, but if you just select all, it'll do all the statistics. And it doesn't really take that much longer to run, so I usually just leave it at all. So I'll run it, and when it finishes, you'll get a table. It'll be right here under standalone tables. Open that guy up. And now we have an attribute table, right? So this is object ID 1, and this is the mean value, object ID 2. So we can sort that. And we can find out that object ID 7 does have the smallest value. Now, what I was talking about in the slides is that I could now join this back to the potential parks data set. So if I right-click on potential parks, and I say joins and relates, and say add join, then it'll open up the add join tool. That's different in ArcGIS than ArcMap. In ArcGIS Pro, it's always a tool. So I could select that I want to join based on the object ID. Okay. The object ID right there. Make sure those are always right. And then now I click run. And now in this data set, I can open up the attribute table, and all that data has been joined into that data set. And I could then symbolize based on that value. Graduated colors, symbolize based on the mean values. And I'd get a very similar map. The colors aren't quite the same. But if I think if I chose, I don't see the same color ramp. It doesn't exist. That's at least closer. Okay. So this is a raster data set. This is a vector data set, but they contain the exact same values now. So that's one example. Just one example from something we already did. So I thought maybe that would make it a little bit more clear. Here's another example. And this example I made it a while ago, so it runs ArcGIS. It runs an older version of ArcGIS, but it still shows how it works. Okay. Well, actually, the example hasn't started yet. This is the last slide on how it works, but this is creating tabulate. This is showing tabulate areas, which I didn't demonstrate. So this will be a good one here. Tabulate areas. What it does is that it determines the so you still got your zone layer, right? So it's a it's in this case it's just different slopes. These are really low slopes, moderate slopes, high slopes, very high slopes. Just think of it like that. Okay. Then you've got your value raster, and in the case of tabulate areas, the value raster must always be an integer. So it's a little bit different. So this has to be an integer value, and what it does is it basically, another way to think about this is you might have heard the term cross tabulate before. It calculates the total number of values in here for each zone, okay? And so the total area of each. So you've got the three integer slope values, 3 of those, 1, 2, 3, and 3 here, you get a value of 36, this is the 3 value. You get a value of 2,700. So that's the total area of 3 areas. Of cells with the value 3. Cells with the value 2, there's more of those. Cells with the values 1, there's the same number of those. And finally, cells with the value of 0, there's only one of those. So 900 times 3 should be 27, is that right? So there's one, so each cell is 900 by 900. I didn't know what the cell size was. So 30 meters. What's 30 times 30? 900. Yep. So 30 by 30, 900. So there's the area of 900 is the area of zeros is 900. The area of threes is 2,700. The area of twos is 3,600. The area of ones is 3,600. Now you may be asking yourself, there's more twos than there are ones, right? But because of these no datas, we see these no datas. It cuts off 2 of these twos and 1 of the ones, and another 2 gets cut off here. So there's 1, 2, 3, 4, 1, 2, 3, 4. So that's what's happening there, just to demonstrate the no data value. So 4 times 900 is 3,600. So instead of getting the mean score or the summary, you get the total area of each type. That's what's called tabulate areas. So if you wanted to ask the question, how much area do I have of 3 or 4 different forest types. This would be the way to do it. Right. But it does cross-tabulate it. So this, you could do a better example here. Let's say we had a second value over here. So this is built up. Let's say we also had open. So we had 2, 2, 2, 2, 2 here. Then we'd have another column that said value 2, and it would tell us that if these were all 2s, the 3s, this would say 0, and the 3 would say 2700 over here in value 2 in column 2. That's what I mean by it's a cross-tabulate. So here would be a more complex example. Let's say we had city boundaries and we had land cover. And we did a cross-tabulation. The columns could be either cities, but it would make more sense to have the rows be cities and the columns be all the land cover type. And so what we could do is say in city 1, there's this much of this land cover, this much of this land cover, this much of this land cover, and so on. It's very much like doing an overlay. That's what I meant when I started that up. Okay. All right. So here's the example. I'm going to start with a tabulated area example here. So we're going to focus on urban development pattern analysis problem. Okay. So this study was conducted in the Philippines. So we're going to look at the distribution of built-up developed areas relative to slope. So we can just skip to the picture here. So we've got our picture here, and here's all of our built-up areas in red. The other areas are no data. Okay? So built-up areas, no data. And we created this data set using a satellite image. We just thresholded it in tropical areas. Basically, if you've got most vegetated areas look different than areas that are built up. Okay. Now, you can't really see all the differences that you might want to see. You can't tell if something is built up and then abandoned, which happens a lot in developing countries, but you can definitely tell if the forest has been cleared and there's something there. Okay. So that's how that was created. Then in another data set, we took elevation, we turned it into slope, and then we created 10 different slope values from low to high. Okay? So these are all of the slope values, 0, 1, 2, 3, 4, just as an integer grid. Remember, it has to be, both of these inputs have to be integer in tabulated areas. Okay? All right? So, then we created we buffered the roads and we created distance from roads. So we have zones that are a 200 meter interval away from the road. So 0 to 200, these are just major roads, by the way. 0 to 200, 200 to 400, 400 to 600, those are also zones. So to actually run it, again, I said that this was old, an old interface. This is ArcMap. You could still pull up ArcMap on these computers. But the input raster, the zone data is the slope value. Okay? The different 0, 1, 2, 3, 4, 5, the integer slope values from low to high. Okay? Then the zone field is just the value, since that's already a raster data set. The raster or feature data class is the built-up map that I created. That's this one. And then this is the output table. So far, we're not using the buffer zones yet. just the first two data sets that I talked about. Then this one right here uses, instead of the slope integer, I also ran it again using the distance from the road, but still looking at the built data. All right, so here are the outputs. The output looks like this. So in this case, what you get is a column that represents each of the slope classes, and then the amount of area that is within that slope class. And so we could chart that. So as the slope increases, so we actually had, we could have theoretically had all the way out to 90, because you can have a slope of 90 or just below 90. So what this is saying is, as we increase the slope, there's less and less built area. So you would have expected that, right? So at the lower slope values, there's not really much of a relationship, right? Because what's the difference between 0 and 1 and 2 and 3? So it just so happens that there are actually more areas at I think it's 4 degrees that were built up than at 0. Because there's not that many perfectly flat areas. But once we get up to there, it levels off, and you can see that relationship. And this is also the distance from the road versus built-up area. So, again, this is something that you might expect, but it's just showing how we could do an analysis and say the built-up area decreases as we travel away from roads. So there could be another relationship that you're trying to establish. But here, we've come up with a way to quantify and to communicate to somebody else the relationship between these two variables. But we got the materials out of a GIS to do it. So the way that I created those graphs was I just took this and I exported it from ArcGIS into a format that Excel could read. Anybody used Excel here before? So it'll read a DBF. So then you just create a line graph from this column to this column. All right, so our lab, we're going to do something like that, but we're going to use this tool, Zonal Statistics as table. Okay? All right, so this is an example for Zonal Statistics as table. So here, we're going to determine the maximum and mean erosion potential for each slope value. So we're saying, okay, in areas that have higher slope, they probably have a higher erosion potential value. Okay? So in order to study this, we'll take slope and erosion potential, and we'll do a zonal statistics as table. This is the output we get. So for each slope value, low slope, medium high, and high slopes, these are the erosion potentials. So the maximum erosion potential is much higher, it increases. The mean erosion potential increases in each of those cases. So that was just a quick example of that. All right. Here is a more complex example. Just skip to the maps because it's easier to explain and to understand the map. So this is our first input map. Here's our erosion potential map. And here is the slope map. Same way we created the slope map before, just turning slope values into integers so that they can become zones. And then here's the municipal boundary file. So each one of these municipalities can also be a zone. So if we ran the zonal statistics as table, we could specify the slopes as the zones and the erosion potential as the value raster, and we would get that chart that I explained in the first, sorry, that, not chart, table that I on the first slide. All right, so zonal statistics as table, we could use the municipal boundaries and erosion potential and find the the average or the total or the maximum or majority value for erosion potential by municipality. So once we calculate it, here with slope we have values ranging from 1 all the way up to 60 something again. With municipality, we only have one value for each municipality, and we have the minimum erosion potential value, the maximum erosion potential value, the range of erosion potential values, and the mean and so on of erosion potential values for each zone. And then if we diagram these, here's just slope and the maximum erosion potential. It doesn't have quite the smooth relationship that we saw before, but in general, particularly if we ignore the very low slope values, it does increase. The erosion potential does increase as slope increases, which is what you would expect. I only have a couple slides on global functions. The best way to think about a global function is that it's basically a zonal function with the entire data set. Okay? So you're creating an output raster where everything is the function of the entire data set. So it's a whole entire data set where everything is a value of 42. ArcGIS doesn't have a built-in tool to do global functions. If you wanted to do it, you would create a data set that had ones for everywhere in your whole data and run the zonal operations on it. All right. Yeah, you got the same thing. Okay. Okay. So there's different syntaxes. Sometimes we separate out operators from functions. A function usually runs in ArcGIS by specifying a number of layers or input values. So you notice for the neighborhood operations, you specify what type of neighborhood and the size of the neighborhood. Those are also other inputs to the function. Whereas an operator like addition, subtraction, multiply, divide just has the operator in the center. Now ArcGIS has actually implemented a lot of these as functions as well. So there is a plus operator that takes layer 1 and layer 2 and adds them together. So there's a function that does the same thing as an operator. And you can use either one in raster calculator. You can run the plus, so you can do the plus sign. All right, this is an old screenshot of the help, but this is just to remind you that we've talked about a lot of different tools. There are more out there, but we've talked about some of the basic tools, and they're all extensions of what we've talked about up to this point. So it's a good idea to read the help. So today, we're going to walk through, I'm going to give you two problems, and we're going to walk through one and kind of talk about how the other one will work. And I want you to be able to go read about the help. Basically, you're going to run zonal statistics table by yourself. So you need, if you need to figure it out, I want you to try to figure it out on your own by reading the help and trying to understand. You can go back and look at the slide, trying to understand which ones need to have the inputs in order to get the answer that you want. All right, so that's the end of the slides. Okay. So, let's do the first part of the lab that I said that we would do, that we would walk through together. Okay. So I'm going to get rid of a lot of these examples and just bring up the data. Actually, I'll just open a whole new map. Insert map. So now I have a map and I can start fresh. All right. So the first thing I'm going to do is actually open up the lab document. So this is the exercise for today. We're going to implement a few different GIS models. They're going to use both neighborhood and zonal functions. And we're going to study the vegetation change in the Keys of Southern Florida. Okay. So to do this, I've given you a number of data sets. I have an elevation data set that you've already seen. I have two images that you haven't seen yet. I'm going to go ahead and add these in. So I go to catalog. I'm going to add in all this data into this other map, even the water. Drag it in, drop it. So now I'm going to turn off everything except for the elevation, these two data sets, okay? So I've got my Keys data. See that? So this is an imagery data set. Does that like look like the right colors? I mean, oh. That's not the base map. This is actually this Keys 2011 image. So I'm going to play around with the band combination here real quick, and see if I can make that look more normal. Oops, that's not what I meant to do. Symbology is what I meant to do. So there are 4 bands. So it's very likely that band 4 is near infrared. And usually that means band 3 is red and band 2 is green. So now we have it symbolized like a typical false color image. So the red represents healthy green vegetation. So let's go ahead and do the same thing to this one. This isn't actually part of the lab, but it'll help you better understand what's going on in the lab. So here I have 2011. If I turn it off, I go back to 2001. So 2011, 2001. Okay. Now there are some obvious differences just in the richness of the data. So 2011 looks like it was acquired on a hazier day than 2001. See how they're hazy? It's a hazier day and there's more variability. But besides that, there are some things that have changed. I think this is one of them. Nope. There is a burn area. I think it's right there. Yep. See that area right there? That got burned between the 2 years. You can see that there's vegetation in it got burned previous to 2001, and it's beginning to grow back. I remember. Okay, so that area right there got burned previous to 2001. Now it's starting to grow back. Okay. All right. You're not actually going to utilize either of these data sets, but I wanted to show them to you because they're how I calculated these other 2 data sets. Now, this isn't a remote sensing course, but this data set right here is what we call the NDVI in 2001. It's a surrogate for elevation. So we used this 2001 data set. This 2001 data set was used to create this image. The high areas are intense vegetation, the low areas, vegetation's lower. This is the same thing for 2011. So if we zoom into that spot that was burnt and that was growing back now, yep, it's right there. See how the vegetation was not very intense. It was a little bit of stuff that was starting to recover from the little bit of vegetation, starting to recover, and now it's pretty much recovered compared to the areas nearby. You can kind of tell there's a little bit of a faint difference in the area. But let's look at that area. There's now there's a big area that is no longer vegetated. See, that's a decrease overall in the vegetation. See if there's any other big differences. There's some small differences. I don't see any other huge differences in the data. Okay, so those are the data sets that we're going to use. And we also have the land water mask. That's the first data set that came up. I don't know why that keeps showing up. Okay, the land water mask is this data set. So basically land is 0 and water is 1. Okay, so we're not going to be using the image processing. They're only coded for reference. So we're going to complete the following 2 tasks. For the first task, I will walk you through it, completing it by creating a raster function chain in class. So we're going to do the first task as a raster function chain. I started to make the lab, but I didn't get there, so we're just going to do it together. Anybody that's not there that had to go, it'll be on the video. So what we need to do is what we need to do is replace the areas of no data that are not water with values that would have been in the focal statistics function. Did you notice that when we did focal statistics, it replaced some of those values out in the void, right? So what we need to do is substitute those values out in the void with the neighborhood values, and that way we can create values out into the void. All right. We'll then use the con operation in addition to the focal. You will then use the con operation in addition to the focal stats operation in order to reassign the values that are water and not voids to no data. Because remember when we ran it, this is in map 1. If we go turn on, create a bunch of different layers here. Here's the original focal mean though. So here's the difference. Look at how it goes out into the water. We still want water to be water, but we want data voids like these to become values. So what we're going to do is first create a data set that is the neighborhood mean, then create a data set that is the replaced voids with the values, and then finally the conditional operation to remove the the water values from the data set. You may understand a little bit better as we proceed through that. So does anybody remember how we, let's do this on map 1. Does anybody remember how we started creating a raster function chain? Which data set do we want to operate on anyway? Yes. Elevation. So we've got our elevation data set, and we want to do a focal mean on the elevation data. Yeah, it's under analysis, and then under raster functions. So we go to raster functions, and the raster function that we want to do is just under actually, it's under correction. Now we're looking for neighborhood. Kernel density.
Statistical.
There it is. It's no, it's not cell statistics. No, that's the second one. Ooh. It might not be in there. I might have made a big mistake. Yeah, we can obviously just use the toolbox. I was trying to. Okay. There is a smoothing one, which is what we want. Smooth arithmetic mean, smoothing 3 by 3. So let's see what happens if we choose it. So that's 3 by 3. Huh. I mean, that's pretty much what we want. Let's do user defined. What's, well, no, that would be it, right? Smooth arithmetic mean. 1/9 is 0.111111111, right? So if we choose the input as the elevation data set, and we create a new layer, let's see if it does the same thing. There's the convolution of elevation. But it doesn't eat into the no data areas like we want it to. So yeah, we're gonna have to do the we're gonna have to do it in Toolbox. Dang. Of course we could do, well, it still won't. It still doesn't look as though we can eat into no data operations. All right. Okay, so let's change the assignment a little bit and just do this in Toolbox. Okay. We can do the second one in, because zonal's definitely there. Do the second assignment in raster function chain. All right, so if we go to, I can change the assignment, but if we go to the Toolbox and we run focal statistics on the elevation data set, it's going to eat into these no data areas like we want it to. So let's choose elevation, just like Elvis said. And we're going to choose a rectangle. Let's name our output focal stats. Let's do 7 by 7, just like we did before. And then run, it'll be mean. Okay. So it'll be like that. It's a rectangle, 7 by 7, and we're going to run it and make sure you leave ignore data, no data in calculations. And what it will do is it will eat into the data voids and give us what we want. See how it ate into the data voids? Okay, now what we really want to do is we want to say if there is a no data value, let it get the value from the smooth data set. But if not, we want to keep the original data. So that's a conditional operator. This is where we're going to make it a little bit of a long statement. So let's do this in raster calculator. All right, so the conditional operator is con. Does anybody remember using the is null operator last week? What does the is null operator do? It's kind of like the conditional operator, right? But the condition is always, is it null? So we could just run that is null operator, I think, from last week. I think that'll work. Let's read about it. Let's read the help. Okay, so it just produces an input and an output. It's actually not going to work as well as I thought. I think the conditional operator is still what we need, because it's just going to produce ones and zeros. All right, let's go back to the master calculator. Okay, so basically what we want to do is say, if there is a value in the original data set, use it. If it's null, then use the data in the other in the smooth data set. What's that? Yeah, I think set null is what we actually used last week, right? So no, because we need to ask, is it null? Not just set it null. Right, but that's exactly what we're doing. So a conditional operator works like this. You say con, and then you say the true raster. No, sorry, the condition, and then the value if true, and then the value if false. So that's the general form of this. So we need to put the condition here, and then we need to put the value of true and the value of false. So basically what we want to do is say, if the original data set is null, then assign the smooth data set. If it's not null, assign the original data set. Okay? So this right here needs to be the original data set. Like this. What's the original data set? That's the elevation. So if elevation is null, so here's kind of I don't know if you, maybe you've not taken a computer science class, but in a computer science class you might write some pseudocode. So if I wrote elevation is null, and then here the value of true, this is going to be the smooth data set, the 7x7 data set. So here, what I'm doing is saying, if the elevation image data set is null, give it the smooth data. If not, give it the original data set. That way, I don't get the smooth data everywhere. I'm not degrading all of my data. I'm just guessing in the voided areas. I'm not guessing everywhere. I'm not degrading my data everywhere. Okay, so what we definitely need to do is make this more correct. And you do that by doing this. So is null. Let's make sure that's the right. So if I hit this button, the help button. And I search for is null. Pretty sure that's the right tool. Sorry, is null like that. All one word. Let's look and see if the syntax is right. It looks like it is. is, and then the n is capitalized too. So something like that. So what this is doing is, this is the conditional, so this is the condition, this is the name of the conditional function. This is the condition, this is the value of true, that's the value of false. So the way you can read this is, if this condition is true, which is saying, if elevation is null, then give it the smooth value, else give it the elevation value, the original value. Okay? Now, I said that we'd have to do one more thing, and that is that if the value was land, then keep the original values. If the value is water, reassign it no data. Okay? So we need to run a set null at the end. But let's run it as two different raster calculator operations rather than making it a big old raster calculator. So this is, we'll have two different if-then statements, but we'll do it as two different runs rather than trying to squeeze it in here. But we could nest them, is what I'm trying to say. We could nest a set null. I'm sorry, we can nest this inside of a set null. But we're not going to do that. It'll be more simple if we do it as two. So I'm going to run this guy. And then once it runs, we'll see if it looks right. Remember, we're not concerned about these water areas anyway, because we're going to reassign these water areas to null. What we were really concerned about, should have renamed that. What we're really concerned about is in the original data set, the elevation data set. Let me symbolize this better. Yeah, that's fine. Turn off the lights. Let's turn the no data. Okay. See these guys right here? These smaller ones? This is a data void. That's a data void. That's a data void right there. Lots of times the LiDAR data doesn't, like deep, dark elevation doesn't show up. So we got a data void there. These are actually probably water, but they're so small that it's okay if we replace them. This is definitely water. Okay. So let's see if we can find any others. So that's all water. We don't really care if that. We're gonna turn that back into no data. Just looking for some more data voids. Okay, here's a couple more data voids right here. Okay, so let's see if those got replaced. So let's turn on the condition data set that we just ran, and yes, they got replaced. So did these areas, but they're going to get replaced. See how they got replaced? The data sets around them, the raster around them is the same, but now we don't have any no data there. We have data there, and it is the average from the surrounding area. Okay. All right. So that was that. Now what we need to do, though, is see this water image? Anything that's water should be a data void. We don't want to include that in our analysis. So we need to take out anything that got a value that shouldn't have, that's really water. See all that water? So this is what we're going to do is set null. So what we're going to do is say, if it's 1, set it to null, else go leave it as the con condition. So in geoprocessing, well, I wanted to run raster calculator. Okay, so we take our set null, and then we say a condition, water equals, is it equals 1? I think that's right. And then if it's true, if water equals 1, we want that to be null. Let's look at the help, because I forgot exactly. Remember last week I also didn't get the syntax exactly right for set null. Okay. set null. All right, so this is the syntax. Your in raster 1 or your in raster 2 value equals 4. So let's see what those are. In conditional raster, in false or constant, and then your where clause. So it's going to set it equal to null if this is true. If it's false, it's going to set it equal to this. This is just optional. We don't really need that. So our condition is the water is equal to 1. That's the true. That's the conditional. And then the false raster would be this one. So now that'll work. So the way we read this is, if this is true, set it to null. If it's false, do that. So it's going to go for every cell. It's going to analyze. That's one of the ways that you can think about, particularly these local operations. This is a local operation. So for every cell, it's going to evaluate this statement. Is this statement true in this cell? If it is, it's going to set it to null. If it's not true, it's going to pull the value out of the condition raster.
So none of the water is one and the same.
Right. It's going to basically, the end result of this process is anything that's null in the water.img will become
True statement we have color never change it.
the conditional statement. All right. So I'm going to call this. This is the final data set. Void filled data or elevation. So now I'm running this, and it's the void filled elevation data. The final result. So there's the void filled elevation. To see that it's correct, we'll have to actually turn off this layer, and let's just turn off everything else. Where's that other? Oh, that's this one. Okay. So now we filled the little voids, like over here. We've also filled the void right here. Remember, there was a void right there, probably because it's like a really dark, maybe even wet pavement, because it looks like it goes down into something. We filled all these little voids. Now this is a bigger void. It's okay that we didn't fill that void completely because it's probably water. But we filled any void that was smaller than 7 by 7. We filled up, which is what we wanted to do. If we wanted to fill bigger voids, we could just do a bigger kernel. Instead of a 7 by 7 kernel, we could do a 12 by 12, 13 by 13, or 15 by 15, but they take longer and longer each time to run. So this one is sufficient for answering this question. Okay. All right. So we did that. We did the conditional operation, and we did a set null. So here it says also you'll need to reinside those areas that are water and not void to no value. We did that through the set null command. All right. Okay, so the second task, which I'm pretty sure you can do as a raster function chain. I didn't realize that raster function chains didn't have those neighborhood operations. So the second task will be to examine the relationship between vegetation changes over a 10-year period. So we're looking at, kind of like the examples from the slide, we're taking 3 different or 4 different elevation zones, and we're going to find out if the vegetation changed more in which zone. Okay. How much did the vegetation change in zone 1, 2, 3, 4, and 5? There's actually 5 different zones. Okay. So the theory being tested here is that in lower elevation, there's more variability in vegetation changes than in the relatively higher elevations. I said relatively higher because, again, we're talking about 12 meters. Okay, so the changes you're going to notice are really, really small. So you might look at, when you finish, you might look and say, oh, well, they're like 0.01 and 0.02 and 0.03. They're that small. Okay? But there is going to be a pattern to them. So you need to first create a data set of elevation zones from the raw elevation values. Your zone should be as follows. 1, 2, 3, 4, 5, and above 6. So how would we take our elevation data? Because remember, elevation data, since it's floating point, we can't use those as zones. But we want to turn our elevation data, actually we want to turn the void filled to elevation data. So we want to take this void filled elevation data and turn it into zones. We've run a tool in this class that will do that. Can anybody think of that? We want to take these data and we want to establish these cutoff values. Well, this would be a pretty complicated vector data. I don't. Yes, we've run a tool called it's called reclassify, remember? We ran that tool. So that's one option, reclassify. So I want you all to run reclassify and get it to work so that you're going to recode it so that anything less than 0 is going to get a value of 1. Anything between 0 and 2 is going to get a value of 2. Anything between 2 and 4 is going to get a value of 3. So you can do that, okay? I'm not going to demonstrate the whole thing, but here's the reclassify. You can hit classify. How many classes do you need? 1, 2, 3, 4, 5. That's all you need. It's 5 classes. So you can hit 5, and then you just need to change this table so that it uses the values that I told you to use, and these are the new values. Okay. Let's see if there's a function chain that does it as well. I'm just curious. I don't actually know. So maybe if I search reclassify, remap. Yep. So we could do it in the raster function chain. So here we've got, -5 is, I said what, -2? Less than 0. I know that there's no values under -5. So -5 to 0 gets a 1. Okay? And then if I'm going to keep going on this, 0 to 2 gets a 2. So 0, 2 gets a 2. Okay, and then this needs to be 2. There we go. And then 2 to 4. So 2 to 4 gets a 3. This should be a 2. And so on. 4 to 6 gets a 4. So I go 4, 6, 4. Keep pressing on buttons. And then finally, above 6. So 6, I know the highest value is almost 12. So just write 12. That gets a 5. Okay. All right, so I just did it as a raster function chain. You're welcome to do it either way. I'm going to actually execute this one. So now look, I've got my values 1, 2, 3, 4, and 5. Remember, with the raster function chain, this doesn't exist on disk anywhere. If I hit save, it'll bring it back up when I close ArcMap and open it again. I can symbolize this differently. I probably do want to symbolize it differently. I want to use unique values. Probably not unique values. Probably classify. And then just have 5 classes. All right, so now the yellow areas are 1s, the light orange is 2, The dark orange is 3. The red is 4. Actually, there's 3 colors of orange there. It's just hard to tell. So those are going to be my zones when I run the zonal operation. Now, I just need to run a zonal operation with this data set on which map? Okay. Yeah, we haven't gotten that far yet, right? I haven't even talked about it. So you will create a raster that's the absolute difference in the NDVI values. So how could I create a raster that's the absolute difference in NDVI values? Using knowledge that you already have, what does it mean to take the difference in the values? Right, subtracting them. So I need to do. We haven't done it as here. Let's see. Let's see if there's a raster function that does subtraction. So math. Yep. There's minus. Is there also? We also need an absolute value one though. Is there an ABS? Yep, okay, so there's both. And then plus there's a calculator. I wonder what calculator does. From a mathematical expression. I'm learning this raster function chain stuff too. So here's our expression, raster variables. I'll have to go read about that, but we could definitely do it by doing minus, right? So we're gonna take NDVI from let's do it the proper way. NDVI from 2011 and subtract to 2001, because what that'll do is it'll make it positive if it increased, which is the way we want to do it. Here we've got like the environmental parameters we can set max of. Doesn't really matter. Both of these have the same exact cell size and extent, so we can leave that. And then we can run this. And our output now is the difference in the NDVI values over time. So you can see this area got dark, which means that it has a big negative value. This area got bright, which means it has a big positive value. This area was burned a long time ago and regenerated. This area must have been cleared, or maybe burned. That's a negative change. This is a positive change over that 10-year period, from 2001 to 2011.
So bright means growth, dark means...
Exactly. That's why I put the most recent time first, because then if you have a big number and you subtract it from a small number, you get a positive number. If you take a small number and subtract it from a big number, you get a negative number, which means it went from big to small. This is negative, that's positive. Okay. All right, now I said the absolute change. So you actually want to, so this is a raster function chain concept here. So if we run absolute, now for the raster function, we want to choose this raster function here as the input. And we can leave those. Those are fine the way they are. Okay. So there's my absolute change. I hope that does take the absolute value. What's that? Yeah, it does. I'm just wondering why this area didn't turn that bright, but maybe those absolute changes aren't that big. All absolute value does is change negative numbers to positive numbers. All right, so anyway, that's the data set that you want to take right here, the absolute value data set that you want to take and run through here. So you basically we've gotten you all the way to the last step, but I want you all to try to attempt to do the last step yourself. The output table should be a table that reports the average change and the standard deviation of the change. So basically you need the mean and the standard deviation. Remember, if you run zonal statistics as table, which I tell you to do, so you're going to run zonal statistics as table, you could run it twice and select standard deviation once and mean once, or you could just run it once and choose all. I don't know if you can do it as a raster function chain, but you can definitely do it in the toolbox like we did it in class. Let's see if there's a raster function. So it looks like it only will create an output. Like it's only doing zonal statistics, not zonal statistics as table. So run it in the raster calculator. I mean, not the raster calculator, the geoprocessing. Yeah, go ahead. Yes, I started with the focal. The output is the focal output. Yeah, that's right.
Is everything built on that?
Yes. Everything's built on that. Yep. Exactly.
So we got to start with that first.
Yes. Now, one more thing I want to say before I let you calculate zonal statistics as table. If you have followed me, and you're wondering, hey, zonal statistics as table, I want to take this data set right here. It's a virtual data set. It doesn't exist on disk yet. Okay? It doesn't show up under here. Oh, it does show up under there. Okay. Never mind. It shows up under there. So ArcGIS Pro has programmed that to do that. But if it hadn't, or if you wanted to make sure you put it on disk, then you could right-click this guy and just say data export raster, and you could save an actual copy of that data set. Because right now it only exists in the computer's memory. So anyway, but you're going to have to run this tool, and you'll run this tool, and what I want you to figure out what goes in each of these. Okay. I've already kind of given you what goes there, but basically you need the absolute difference there, but you need to figure out what goes in the other ones. All right, and then let's go over the deliverables, and then I'll cut you loose, and you can ask me individual questions or questions as a group. Okay, so what are you going to turn in? Okay, so I want you to go back. You can go back and watch the video if you want, or you can just go back and think about what we did to create the map. I want you to do a flow diagram of the process you use to complete each task. In other words, draw a box or a circle for each tool that you ran. And say, I ran this one first, and then draw an arrow to the second tool, and I did this one second, and so on. All right? So what did you do for the first process, and what did you do for the second process? So there's two flow diagrams. So you can either draw a hand drawing, or you could actually recreate what we did in Model Builder. And we already discovered you can't do the first one in raster as a raster function chain, but you could recreate it in Model Builder and give me a screenshot of that. You don't even have to run it, you just throw it out there on Model Builder. Okay? All right, then you're going to have a map composition of the three things. The void filled elevation data set, that's from this one, that's the void filled elevation data set right there. Then the elevation zones data set, that would be this one. So I want a map of that. And then the absolute change in NDVI raster, that would be this one. But your map should be zoomed out. I just wanted to include at least Big Pine Key, which is this one right here. So you could make three maps like that on the same page, or you could just do 3 portrait pages of those 3 maps, or 3 landscape pages. But I think it would fit better on a portrait. Okay, and then finally, I want you to make a plot / graph of the standard deviation of the NDVI difference by zone. So once you run the tool, this zonal statistics as table, you're going to have a column that has standard deviation. There's only going to be 5 values. There's going to be 1 for zone 1, 1 for zone 2, 1 for zone 3, and 1 for zone 4. So even if you haven't used Excel before, you can do this in like 3 seconds. So let's say we've got zone 1, zone 2, zone 3, zone 4, and zone 5. You can export right from ArcGIS Pro to like a DBF or a TXT, or you could just cut and paste all the values. There's only going to be 5 of them. And then let's say your standard deviation values are something like this. I don't even know if I forgot exactly what the values are. And actually, I think they go the other way. But anyway, let's say they look like that. So then you just highlight both of those columns, and you can create a chart. Insert. No, it's yeah, charts. Sorry, there it is. I was like, these look like charts. Okay, insert. You could do a bar chart, or you could do a line chart. Either one would be fine. Probably line chart would make a little bit more sense in my opinion, but do what you want. We actually don't even need this column right here. That's actually the labels. So here we've got our bar chart. See how it put those by default? 1, 2, 3, 4, 5. So we just actually need to highlight that column, and that shows the standard deviation changing for each as the elevation increases. So if you want to try to put a label on each axis, you can. So experiment. You could read about. You could read the Excel help to do that. What would this axis be? It's actually X, right? But what would the label for this axis be? What do these numbers represent? Those are, yes, they're the elevation zones. So elevation zones. If you wanted to, you could even label them, under 0, 0 to 2, 2 to 3, 4 to 5, 6 and above, or something. I forgot exactly what they are. If you went back and looked at the lab, you could label those that way, but you have to look at the help. Or you could just label it as elevation zones, increasing elevation zones. Okay? What's the y-axis here? Yours is going to be different. It's not elevation. It's the standard deviation of the vegetation change, or the standard deviation of the NDVI change on this side. So you can just write vegetation change or something like that. All right. Yeah, I'll stop there, and really it's not too hard. Okay. Most of it is just going to be trying to figure out how to run this zonal statistics table to get to the answer that you want. So when you run it, if you have a table that has values 1, 2, 3, 4, 5, 5 and 6, or just 5, right? 5, yeah. 1, 2, 3, 4, and 5. Then you're good, and it has a column that has mean and a column that represents standard deviation. I should have actually had you turn in the values themselves too. But I'll see them on the chart. Yeah. So. All right. Yeah, I actually mistyped this. It should have said standard deviation and mean. So like this is actually what I wanted, but I won't change it. But like if the mean might have gone like this. It's actually I think going the other direction, but you could create a chart that had both of those on there. That's actually what I planned for the assignment in my head, but I just said to plot the NDVI. So we'll just leave it like that.
So you're saying I had a mean and standard deviation.
That's what I had planned to, but I messed up when I typed that sentence. So. All right. Cool. I'm going to stop the video now. Anybody have any general questions about the lab, what's expected? I'll actually leave that on the video. Okay. I'll stop the video. I'm going to get a drink of water, and then I can answer any questions anybody has.